Hello and welcome to video number 26 about how to make a chess program in Go. Today we will start with something really interesting. So far we have done nothing that takes a risk. If you want to win, you need to take a risk, and that's what we will do now. But the gain is huge. And what we will do today is null move pruning. A null move is to make no moves and hand over the turn to your opponent again. And that is of course not allowed in chess, but you can use it in your thinking process, of course. And the idea is, if I don't make a move and you cannot increase your score, then your position sucks, or the opposite, my position is great. So let's go coding. Okay, we can start to remove this. We have already made these, and now we work with the null move. First of all, I will remove some comments here because I prepared this long time ago. So what we are doing here is, so if it's a PV node and best move is a no move, meaning that not a no move, meaning that we are in this first move in the PV node, the first child, then we make a search with just a null window, and that has nothing to do with null moves. It's just a window with one step. You see, minus alpha, minus 1 up to minus alpha. If we get a score greater than alpha, then we need to make a research. It didn't turn out as we thought. In other cases we search with a wide alpha beta, a wider alpha beta I should say, but often these alpha and beta even here are only a null window, alpha beta window, because of that the parents are working with the null window. The null move pruning is more or less the first thing we will do in the search function. So let's put it here. It's before the move loop and everything. Null move. Okay, we need two variables to work with. One is if we are in check. And it's attacked, our king attacked with opponent side. And the other one is evaluation, this position's evaluation, and we need the correct sign here for color. So, and let's see the null move pruning here. So what we don't want is, if it's a null move, we will not make any if it's a PV node, we will not make any null moves. We don't take risk in the PV node. If we are in check, we will not make any null moves. It doesn't make sense. And there are some other conditions. For instance, there are two very important conditions, and they can be very hard to detect. One is if we are in if it's a stalemate, so we cannot make a move, and stalemate, that is a draw. But in this situation, if we make a null move, we will not see that it is a stalemate, and that will give us invalid information. The other one is Zugzwang. You can make moves, but every move is a disaster. it's a situation where you wouldn't like to, where you really would like to have a null move, and skip your move, because every move will be a disaster. And both stalemate and Zugzwang, there are very typical themes in the end game, and they can be quite hard to detect here, but we'll try to do in some way. So not the PV node, and the depth. The depth must be greater than 0, because you will see why later. And then if it's a mate score, should be mate score there, then we know that we are searching for mate, and we will not try any null move in that case. And if we are in check, or we will not do it. And here is the thing with evaluation. Let's say the evaluation that we make here is less than alpha, and then we make that we see that, okay, the opponent could not increase the score. So what? We cannot make use of that information. It doesn't help us. And if the evaluation is between alpha and beta, then it's a PV node. So we will not make any null move anyway. So only if evaluation is bigger or equal to beta, we will make the null move. And if the opponent cannot increase the positions, then we can just prune the whole thing. And then let's say we call that anti-null move, the thing with stalemate and all that. So let's start to set the null move. We make the null move. We don't have that yet. Basically, it's just change the color. We start with a minimum score, and if depth is less than 3 or equal, we cannot, because we will reduce the depth. So, and we cannot do that. So we just make a QS search here, like this. Maybe we should have some gain, some bonus here. I'm not sure. I have to think about that. Some bonus for the opponent. Okay, in normal case, then we search from beta to minus beta plus 1. That means they need the opponent need to have a better result than that. And the depth is reduced. That's the gain here from null move, that we search much lower depth. And something is missing. Oh, it's the board. Okay, board start. So after that we will undo our null move. We take back the Saito move, and if score is greater than or equal beta, we can save this in the transposition table. We have no move, but we can do that anyway. We save the score. Like so. Okay. And here we can return, because they couldn't, or the opponent didn't get a score greater than beta. This is not correct, right? It should be here. Okay. We have a few functions to make. One is the null move, to make a null move, and we return a move. So because we will pack this, we have no move, but we pack that because we want to save the EP square, the state of the EP when we make or undo our move. We can save the castling as well. Castlings. Okay, it's not necessary to save the castlings, but let's just save that. I need this. Let's paste in the board struct here. So we will set the EP to 0 and flip the key and side to move like this, and we need to return the move. Okay, and we copy this one for undo. We need the move and remove this one, and we set EP back to its original value. Can remove this, and we also flip key and side to move as before. I don't need any pack move here, and the EP should be the last thing we do. Okay, we have one more move to fix, one more function to fix, and that is anti-null move. So is this a position to avoid null move? We need the board struct there. Return bool. Okay, what do we need here? I think at this point we only check if it's only a king on the board for this side to move, because I think we could, I will not do it here, in the future we could take pawns as well and see if the pawns are immobile. We just shift them one step forward and see if they can do a move, because that is also a typical stalemate or Zugzwang, or could be. So if the only thing we have is a king, return true, otherwise false. And back to the null move, and let's call this is anti-null move, and it's a method to board. So I will make performance tests now, and we should see a big difference. And here we are. We can see what's happened with the null move. It's a huge difference. If you compare the start position, for instance, or any of the 4 positions. The difference is a factor of 50, 80, things like that. 100 for the London position. And the reason is that the effective branch factor went down to, well, I think around 3 should be correct. The node per position is not as fast as before, but who cares with results like this? So by taking a risk with stalemate and Zugzwang, we can get this enormous gain in speed. And depth has no real meaning anymore, especially after the next thing we implement, late move reduction, that we take the next time. Maybe I will change the time instead of depth when I do these tests. And here are the 4 positions in case you forgot them. And I think we are finished for today. And until next time, have a good time unit.